Let's learn about trig identities. Protect yourself from identity theft. On our agenda, we're going to look at an opener. We'll learn about why do we need to learn these identities, what are the trig identities, and how do I use the trig identities. So let's get ready. You need notes and a pencil. You're going to take a lot of notes, and I'm going to ask you to write down each identity along the way. I will give you an identity sheet, and you will be able to use that on the quizzes and test, but I want you to get this into your own notes as a way of learning. So let's look at this opener, and it's the first quadrant, and it is the unit circle because I have a radius of 1 out to here and a radius of 1 up to there. Also a radius of 1 out to here. If I drop that, my height is my sine because my radius is 1 and the width is cosine. So we're familiar with this right triangle on the unit circle. Let's take a look at this right triangle here, this little bit bigger one. And I'm going to actually go back to the red one for a minute. With the red one, and we know our hypotenuse is 1, it's a right triangle. I could do the Pythagorean theorem and say that sine squared theta plus cosine squared theta is going to equal 1 squared. So now on this new yellow triangle, this is 1. This piece is 1, and this is tangent. So I can say 1 squared plus tangent squared theta is going to equal secant squared theta. And let's look at one more. Let's look at this upside down one up here with a 1 and a cotangent, and then we've got this whole thing, which is the cosecant. So we can use the Pythagorean theorem to do 1 squared plus cotangent squared theta equals cosecant squared theta. Also important to note, notice where I put that square. I'm going to talk about that a little bit later. So these are all versions of the Pythagorean theorem. So it's going to lead us to being able to solve trig identity types of questions. We're not going to solve it in this lesson. It's going to take us a little bit longer, but eventually we'll be able to solve something like this. We're going to start to use trig identities. So trig identities are used to establish other relationships among trig functions to make it easier or possible to substitute things in and make them able to be simplified further, then eventually solve. So today we're going to learn trig identities, and the next class we'll talk about what verifying a trig identity means. So what do we know about trig already? We actually know a pretty good amount. We know all of the reciprocal identities. So take a minute to write these. I like to write them in the 2 columns. So we have our sine, cosine, and tangent. Those are the reciprocal of cosecant, secant, and cotangent. We have the quotient identity. When we think back to the unit circle with a radius of 1, and then we talk about the height being sine and the width being cosine, and tangent is opposite over adjacent, we have that the tangent is sine over cosine, and then the reciprocal of that would be the cotangent, so that is the reciprocal as well. And just a little joke that singerine over coserine equals tangerine. Let's talk about those Pythagorean identities again that we looked at. We have these 3, and these are going to be used a lot, especially this first one. That's a very common one. So my little joke says, I wish I were a sine squared and you were a cosine squared, so together we could be 1. Make sure to get those in your notes. So remembering complementary, the word complementary angle from geometry. What is the complementary angle to a 60-degree angle? That would be 30. How do you find it? You do 90 minus 60. And what is 90 degrees in radius? It is pi over 2. And if you remember, we've graphed sine, and that took us out to 2 pi. And then we graphed cosine, and they were a difference of a half pi. They're a half pi away. We didn't graph the other ones this year, but they are all very similar. So if we think about co-functions, we think about the word complementary, complementary meaning 90, and now we think about 90 in terms of radians. We have all of these co-function identities. So take a minute to write those down. What do you remember about odd and even functions? I briefly introduced this and we said that cosine was the one that was even. If we think about the cosine graph, it starts up and it goes down, and then if I were to go backwards, it looks like that. So we say that it is symmetric with respect to the y-axis, and that's what makes it even, and its reciprocal secant. They are both the only even ones. So that means that the cosine of the opposite of the fraction, opposite of the angle, let's say that, opposite of the angle is the same as the cosine of that angle. And same for secant. But if you're looking at sine and you're doing sine of the negative angle is the same as the opposite, or the reflection. So you'd have to reflect the graph in order to get it to look like that sign. So that's what we have for odds and even functions. Go ahead, record those. So some tips as we start to simplify. Remember to determine the quadrant. We can use this little thing to determine if they are positive or negative. That's what they mean. Simplify all of your radicals, rationalize your denominators. Write the identities in words first and then substitute. We may have to factor and then cancel. Let's use the word simplify. We may have to take a square root, so we'll remember the plus or minus. We may have to do our special right triangles, 30, 60, 90s, and 45s. We'll see those along the way. And you may have to find the hypotenuse using Pythagorean theorem. Just a quick little piece, I mentioned this earlier. What's the difference between sine squared x and sine of 2x? Well, it's just the placement of the 2, and just be careful with your handwriting. Is it an exponent? Is it just an integer in there? Because the first one means sine squared, sine times sine, but the second one means sine of 2 times the angle. Let's try an evaluating question. Let's find the cosecant of theta. If the cotangent of theta is 4, we're told that theta is between pi and 3 pi over 2. So first we'll think about what quadrant we're in. So remember that pi is right here. So we're talking about quadrant 3. Cotangent is positive, but cosecant, which is the reciprocal of sine, we need to make sure that's going to be negative. So I'm going to draw my reference triangle, with that being theta, and cotangent is the reciprocal of sine, so that would have been 4 over 1, but it's going to go this way, so 1 there and 4 there for cotangent. And then they are in negative x and negative y, so I'm going to make them negative. I'm going to do the Pythagorean theorem to figure out my hypotenuse, and it comes out to be the square root of 17. Remember, that will stay positive. So I want to find the cosecant, which is the reciprocal of sine. So if I think of sine, the sine of theta is negative 1 over root 17. So the cosecant is then going to be negative root 17. Simplifying a trig expression, and this is what we're getting to. So if I look at this, and I'm going to think about the trig identities that I just learned, and then the algebra that we have. I have 2 terms here. They both have a sine x, so I'm going to factor. I'm going to factor out a sine x that leaves behind cosine squared x minus 1. And then I see a cosine with a squared with a 1, so I'm thinking about my Pythagorean identity, that's cosine squared x plus sine squared x equals 1. And if I solve that for cosine x, that's 1 minus sine squared x. But we need, no, let's go back and solve for sine squared x. Sine squared x equals 1 minus cosine squared x, but it's not quite the same. But if I divide everything by a negative 1, negative sine squared x is going to then be negative 1 plus cosine squared x, and that's what we have. So I can substitute that in there. So I have sine x is times negative sine squared x, and I get negative sine cubed x. And that would be the simplified version. Nice job.